So for the last couple of years, I've been showing the movie The Martian to my high school and AP Physics students. And this year I decided to publish those lessons on YouTube for other students of physics to see. And also what I decided to do is to provide a report card on the Martian movie, the report card on how accurate the physics is. And here's what I came up with. So for their estimate of the time of flight from Earth to Mars, I give them an A. For the part where the commander is sucked into the tube, there's no apparent force which would provide for that, so I give them a D. The windstorm, a D. Gravity on Mars, a B. Artificial gravity, a B. Air pressure differences, outside versus inside the hab, a D. Gravitational slingshot, an A. Flight without a nose cone, a tarp in the place of the actual nose cone, a D. The Hermes slowdown thrust via air ejection, a D. The spacesuit thrust by Watney to increase altitude, a D. And then the escape velocity from Mars calculation, an A. Now I'm going to go into great detail for each one of these, including relevant physics, the physics equations, numbers, and the relevant applied mathematics. So if you are a student of physics, stick around. I think you'll learn a lot. If you're not a student of physics but want to become one, stick around. Before I do that, I'm going to plug my book. The book is called Physics for Space Travel. It was recently published. It's currently available on Amazon. Endorsed by 3 NASA professionals, and it includes the physics of orbital mechanics as well as rocket aerodynamics. So from the book, you'll learn how to design, simulate, build, and launch a rocket, as well as to plan a mission to a planet in our solar system, or the moon, or intercept the International Space Station, compute the relevant mathematics, and then actually fly the missions using 2 available free simulators which can be downloaded. Okay, the windstorm. I give Hollywood a grade of D for the windstorm. Question is, could a sufficient force be generated to blow really heavy things around on the surface of the planet? And they mentioned 8,600 Newton wind. This is 3 minutes 36 seconds into the movie. So the short answer is no, the air on Mars is too thin. So here is a little more detail. Define momentum as the mass times velocity, where mass is some amount of air. Force is the time rate of change of momentum. So we'll set 6,800 newtons equal to the change of the momentum here, mass times velocity of the air, divided by the time over which it takes to bring the wind to a stop. Okay. The next thing I'm going to do is I'm going to replace mass here with the density of the air times a particular volume of the air. Okay, so I replace mass here with that product. So on Mars here, I'm going to use the velocity of the Mars wind, and this is the density of the air on Mars. Okay. On Earth, it's the same equation, except the density is that of Earth air, same volume. And then of course the velocity of the wind on Earth, divided by the same delta t. Again, delta t is the time it takes to bring such wind to a stop under a force of 8,600 newtons. What I'm doing here is I'm replacing the density of air on Earth with 100 times the density of the Mars air. Okay, that's the factor. It's 100 times greater on Earth than on Mars. Next thing I do is a little algebra. I divide equation A by equation C. Most of this cancels, and you end up with this expression. So the velocity of air on Mars divided by 100, and that'd be the equivalent velocity of such air on Earth. So for example, a 40 mile per hour wind, which is possible on Mars, would be equivalent to a 0.4 mile per hour wind on Earth. Okay. So let's take this to a really high wind, 100 mile per hour wind on Mars, and I don't think that's even possible, but let's say it were. That would only be equal to a 1 mile per hour wind on Earth, and that's definitely not enough to blow heavy things around, even at 0.4 gravity, right? The fact that objects weigh a little bit less on Mars because there's less gravity on Mars due to the smaller size of the planet. Gravity on Mars is 40% that of Earth, so Hollywood got that right. I only gave them a B because I felt that the motion of Watney as he moved around on Mars didn't look any different than it would on Earth. It should definitely look a little bit different since he's lighter on his feet on Mars, but I know that would have been difficult to pull off. They did make, this is 35 minutes into the movie, they did make it appear that a pretty heavy object seemed kind of light to Watney, okay? So why are things lighter on Mars versus Earth? Well, it comes down to the acceleration due to gravity, okay? And from Newton's equation for gravity, you can divide both sides of the equation here by some mass of interest, and you end up with this equation. So acceleration due to gravity, and this is on Earth, be the mass of Earth, the mass of the planet Earth, times a constant g divided by the radius over Earth squared. This is from my book. But this is Mars, so we're going to put the mass of Mars here, which is 6.39 times 10 to the 23rd kilograms. Here's our constant g. And then the radius of Mars is 3389000, and we're going to square that. So we get 3.7 meters per second squared. Acceleration due to gravity on Earth is 9.8 meters per second squared, or if you want to work in feet, it's 32 feet per second squared. So there you have it. Acceleration due to gravity on Mars is about 37% that on Earth. So for example, a 10-pound object would weigh only 3.7 pounds. So again, do they appear lighter to Watney here? Again, they do at minute 35 when he's moving some heavy object. So again, I think that was pretty well done. Person being sucked into the tube. This is, I give Hollywood a D for that, for their physics. So at minute 57:46 into the movie, the commander is moving through the Hermes spacecraft under 0 G, so she's just kind of floating through the tunnel there. And then she moves right, it appears to be sucked into another part of the ship. And that part of the ship happens to be rotating. And yet there is no apparent force which is providing for this acceleration of the commander. There's no air pressure differential. And we know this since people are breathing without a breathing device on all parts of the ship. It cannot be centripetal or centrifugal force, which is a contact force. You must be in contact with the rotating object to experience such centrifugal force. So there's no explanation for why she would have made that turn and then appear to be sucked into the tunnel. Okay, what about artificial gravity? So you'll notice in parts of the ship, they're just walking around as if there's 1 G, like there is on Earth. And now, how is that possible? Well, if you notice, this part of the Hermes spacecraft is rotating. The acceleration due to rotation is called centrifugal or centripetal acceleration. It's given by this equation, v squared over r, where v is the velocity, tangential velocity of the rotating object, and r is the radius, right? The radius of the circle for which it's moving in. Since r times the angular velocity is equal to linear velocity, you can replace v here with r times omega and solve for acceleration. So this is the rate of rotation. It's called angular velocity, okay, right here. So looking at the Hermes, I estimated the radius, this part of the ship, to be about 15 meters. I put the acceleration at 1 G, right? That would make them feel like they're at home on Earth, and that's 9.8. And I solved for the angular velocity, this omega here, and that came out to be 0.81 radians per second. So you convert that to revolutions per second by divided by 2 pi radians per revolution. That gives you 0.13 revolutions per second. So I looked at the movie and I noticed that it took about 24 seconds or so for this part of the ship to make one complete rotation. If you take the inverse of 0.13 revolutions per second, that gives you 7.7 seconds per revolution. So they were off by quite a bit, but I didn't mind that very much. The fact is, you can create artificial gravity through rotation. You have to be located at this part of the ship. And you'd be experiencing that force away from the center. Kind of like a centrifuge. In a centrifuge, you sit down and it starts to spin. and you feel compressed against the back of the centrifuge. Or the ride at amusement park rides, where you're staying in this drum, it starts to spin, and then the floor drops beneath you, and it's the centrifugal force. Some might call it a centripetal force due to the normal force of the wall on your back, which keeps you moving in that circle, but you feel pressed against the wall. So the astronauts and the crew would have felt pressed against the floor, and again would have given them the sense of 1g of acceleration. They would have felt at home as if they were on Earth. So again, I think they got that right. So grade of B. So there's one of the crew members upside down. So it's rotating this way, right? So she's feeling a force away from the center. So she appears upside down, but she's feeling 1g of force. Now, if they couldn't see outside, they couldn't see other parts of the station, they wouldn't even know that they're rotating, right? They would just feel like they're just walking around some room. Okay, the Hab patch physics. Okay, I remember this part of the movie where the entrance to the Hab explodes, and Watney repairs it with plastic and tape. And so that appeared odd to me, and also appeared odd to my students. So I decided to run some numbers, and so I came to the conclusion that that's just not going to be possible for plastic to hold the air pressure difference between the outside and inside of the Hab. After he put the plastic cover on, he got the pressure back up to approximately 1/100th atmosphere, and outside of the Hab, you've got that low air density on Mars, so you have air pressure of 0.1 that of the Earth atmosphere, and so that pressure differential would result in a huge amount of force from the inside pushing towards the outside of what I estimated to be 90,000 pounds. So here's the math. The air pressure on Earth is 14.7 pounds per square inch. However, the Hab pressure is a little bit lower than that. You can see it from the gauge, 12.5 pounds per square inch. You can see that at 15:53 into the movie. And yet on the outside, again, due to the low air density of Mars, the PSI is only 0.095. So take the difference in the air pressure between the outside and inside of the Hab and multiply it by the area of the entrance, okay, which I estimated to be, it's just pi r squared, 7238 square inches. So multiply 7238 square inches by the difference in the pressure, 12.4 pounds per square inch, and that gives you 89,751 pounds. So obviously if you put a weight of 89,000 pounds against that plastic from the inside, it would just blow through the outside. So that would have created a real problem for Watney. He would have had to somehow design something that could take that kind of force, to keep the air inside the Hab. Was a tarp as a nose cone on the MAV sufficient to protect Watney? Okay, so I'm going to give the Hollywood physics grade here a D. This is 150 into the movie. Okay, so again, was a tarp as nose cone on the MAV sufficient to protect Watney? No. Okay. The drag force due to the speed of the MAV in conjunction with the air on Mars, albeit thin, would have been sufficient to tear the tarp and expose Watney to dangerous forces as he ascended up in the MAV. So here's the drag force equation. It's 1/2 drag coefficient, air density, cross-section area times velocity squared. So the air density I used in this example was 0.015 kilograms per cubic meter. And the reason I used that instead of the actual 0.02 or so was because at 10,000 meters, right, it drops. Air density drops with height, with altitude. Okay, I used a drag coefficient of 1.75, which is that for a parachute. The cross-section area of the nose cone I estimated to be pi times 0.6 squared. So I'm estimating the radius of the nose cone to be 0.6 meters. So the cross-section area is 1.1 meters squared. Okay, so yeah, so the tarp was up here on the top. Okay, so as the thing ascends, it starts to experience really high velocities, and even though the air is thin, when you plug really high velocities into this equation, you get really high drag force. So before I can plug all this into the drag force equation, I need to figure out the velocity of the MAV at 10,000 meters. Okay, so that's what this is. From Newton's second law, you can derive these two equations. This is 2 times acceleration times the altitude. Okay, so after 10,000 meters, how fast is he going? If he's traveling at 1.5 Gs. So 1 G is about 10 meters per second squared. So 1.5 is 15 meters per second squared. Plug all that in and take the square roots, 548 meters per second. So I also computed it at a higher number of Gs because I wasn't sure how fast the MAV would accelerate on its way to orbit. 1.5 is the acceleration of SpaceX's Falcon Heavy in the first couple of minutes, actually in the first minute. So I went 4.4 that because it was stated in the movie that the MAV would be accelerating at about 10 Gs. Okay, so again, the argument is if in the first couple of minutes, SpaceX, actually the first minute, SpaceX is accelerating at 1.5 Gs, then the max of 10 divided by the max of SpaceX up here at 3.5 would be 2.9. So in general, the MAV would be accelerating at 2.9, greater than the SpaceX Falcon Heavy rocket. Okay, so when you multiply 2.9 times 1.5 Gs, you get 4.4 Gs. So again, this is the upper limit. Maybe this is a more appropriate number of speed at 10,000 meters, and this would be a lower limit, 548. Okay, so at this point, I've got everything I need to plug into the drag force equation. So 1.5 Gs, here's the speed at 1.5 Gs, 548. I'm going to square that, multiply by the rest of this, and you get 4336 newtons. That's 974 pounds. At the upper limit, you get 2855 pounds, or 12,702 newtons. So these are really large forces, but are they large enough to tear through the tarp? And I would say they are. I was able to find this online. This is strength of various materials. So nylon is stronger than a canvas, right? So the tarp, I'm assuming, is some sort of canvas, but this is, you know, it's probably industrial strength. So even at 475, right, which is one of the stronger materials, this is in newtons, that would have been easily torn by somewhere between 4336 newtons and 12,700 newtons of force. Okay, so again, based on this analysis and the strength of the material, it's pretty clear that the tarp is not going to hold and that Wani's going to be exposed to these really high forces. Now granted, he's got a pressurized suit on and it may not have killed him, but maybe it would have. It at least would have tossed him around, maybe even loosened him from his belt, right? 2855 pounds. That may have been the end for Watney. Mars time to get there. So this is an A, right? So I don't think you can see him very well. That's Teddy, right? The head of NASA in the movie. So he said it would take 9 months to get to Mars. And that's about right, using something called a Hohmann transfer. I thought the movie lacked a little bit of creativity because you can get to Mars, you can leave right now for Mars if you've got a spacecraft ready, right? You don't have to wait for the Hohmann window to open up. Go there at any time. But again, you got the time right, so I'd say an A for that. So this is what a Hohmann transfer looks like. Earth is here. Mars, say when Earth is here, is here. And this would be the transfer orbit, okay? So the spacecraft leaves Earth, provides for a sufficient thrust, which you can compute, and enters into this transfer orbit. And when the spacecraft gets to this point, Mars will be there at the same time. So all this can be computed and timed perfectly, okay? Once it gets here, the spacecraft fires a thrust in a direction opposite to that of the velocity vector, and will fall into a Mars orbit. This window opens up every, I believe, 2 years, okay, and then it takes 9 months, right, to travel this path right here. So it's 1/2 of a transfer orbit. Okay, so you can compute the semi-major axis of this transfer orbit, which is equal to this distance, right, plus this distance divided by 2. That's the semi-major axis. And then you can plug it into Kepler's third law, okay, to compute the period of the orbit. The period of the orbit is 4.48 times 10 to the 7 seconds. And then if you take half of that, that's right, half of this in seconds converted to months is about 8.6 months. So again, I thought that was accurate. But again, they could have gotten there sooner, likely could have gotten there sooner, because, like I said, you can leave at any time if you've got a spacecraft ready. And this gets to something called the Gauss Problem. It's a famous problem in mathematics, and here's how it goes. So here's the sphere of influence. One travels from, say, Earth to Mars, and the sphere of influence is just the dominant gravitational force, and that would be the sun. So it's in something called a heliocentric orbit because it's in an orbit about the sun. All right, so if you know these positions, right, the position of Earth relative to the sun, the position of Mars relative to the sun, and you know the time of flight, right, you can enter the time of flight as a variable, then Gauss figured out how to compute the departure velocity vector and the arrival departure velocity vector. So now you've got a trajectory for making it from Earth to Mars. Okay, so given that incredible accomplishment by Gauss, I used Orbiter 2016. I use this in my book, and you can fly these missions if you buy my book. Again, a plug for my book. But for example, at this particular time, Earth was here and Mars was here. Okay, if you would have left at that time, you would have needed a speed of 77,000 meters per second to intercept Mars, and you would have intercepted them right there. Now, of course, we can't travel that fast. But this was a futuristic movie, a little bit, right? If you looked at NASA, it looked like it had evolved quite a bit. And look at the Hermes, how advanced that was. So it seems to me by, given the technology of this movie, they could have traveled at 77,000 meters per second. If you said I want to get there in 1.5 months, then the speed drops a little bit. Okay, so now you get your departure velocity down to 26,000 meters per second. Our current max speed in space is 11,000 meters per second. But again, you know, we can't do that with our technology now. But in this somewhat futuristic movie, maybe they could. It would have been cool to see them use the more advanced technology to leave at any time, you know. But maybe that wouldn't have made the movie as interesting, knowing that they would take 9 months to get there, create all sorts of problems for Watt, and he had to survive a long time until the ship arrived. Okay, so anyway, enough of that. Okay, next, can the exploding part of the Hermes spacecraft cause it to slow by 30 meters per second? This is 1 hour 59 into the movie. So I did the math, and so the answer is no, not even close. The escaping air was sufficient to slow the speed of the Hermes by only 1 meter per second, based on some calculations I'll show you here in a second. So I give Hollywood a physics grade of D on that one. Okay, so again, in the movie, after burnout of the MAV, the relative velocity between the Hermes and the MAV was 42 meters per second, and that was too fast, the commander thought, for them to be able to properly intercept with Watney and bring him on board. So they felt that if they got it down to 12 meters per second, they'd be okay. So they needed to reduce the speed of the Hermes by 30 meters per second, and they did that by exploding part of the craft and having the escaping air slow the Hermes. You can hear a couple images from the movie. This is the part of the ship where the air went out, right? So the air goes out this way, and the ship will go that way, or the thrust will be in that direction, thus slowing the ship. Okay, so here's the math. We can use a really simple idea called conservation of momentum to compute the change of velocity of the Hermes given the escaping air velocity. Okay, so this is the equation you want to solve. The mass of the air in not only the capsule, but it also evacuated from other parts of the ship, times the velocity of such air. Okay, so that's the momentum on the left side of the equation. And that would reduce the momentum of the Hermes. So as it escapes this way, the momentum change will be in that direction for the Hermes. So if you know the mass of the Hermes, you can compute the change in velocity of the Hermes. So that's what this is right here. So I estimated the air. What I did was I found, here's an image of the International Space Station. And I said, let's assume that the mass of the Hermes is about half that of the International Space Station. If you assume it's equal to the same mass, you basically get the same number, so it doesn't really matter. But I went ahead and let's assume it's equal to half. So that's the mass of the Hermes, 210,000 kilograms. The mass of the air leaving, let's just say the volume of the space station would be about 553 kilograms, and I'll show you how I computed that in a second. times the velocity of the escaping air. Okay, and this was derived from the Maxwell-Boltzmann law, and it assumes minimal interactions for a gas moving freely in a container. So it's a pretty good estimate of the velocity of air in a very low density container. Okay, and then I also assume in the calculation of 422 that the air is nitrogen gas, which makes up 70% or so of air on Earth, and that's the kind of air they've got on the space station and the Hermes. Okay, so when you solve for this, you get a change in the velocity of 1.11 meters per second. So that's a long way from 30 meters per second. That's just not going to get him there, which means that Watney doesn't get rescued. Okay. Then I said, well, maybe I gotta find an upper limit for the escaping air. And I found a really interesting statistic. The fastest nitrogen gas molecules in the upper atmosphere of Earth moves at a velocity of 3108. Okay, the previous calculation was on average, right? Velocity of nitrogen moving in a sparsely dense container. But again, I wanted an upper limit, so I plugged 3108 meters per second into this equation, and I still got way below 30 meters per second. Okay, 8.18 meters per second. Still very far away from 30 meters per second. Okay, how did I compute the mass of the air in the Hermes? So I use this really useful equation. Mass is equal to the density of the air times the volume. So the cubic feet of the space station, this is pressurized volume, is 32,333 cubic feet. So again, I took half of the mass in the prior computation, so I took half of the volume in this computation. So it's about 16,000 cubic feet. I need to convert that to meters because I'm using function of meters in other parts of the equation. So this is the same thing as about 16,000 square feet, or cubic feet. It's the same thing as 453 cubic meters, 35 cubic feet per cubic meter. So the mass of air inside this volume would have been 553 kilograms. All I'm doing is multiplying the density of air, right, on Earth and on the ISS or the Hermes times the volume of air in cubic meters. So 553 kilograms. Again, that's how I got this number right here. Okay, next. Watney closing the distance between him and the Hermes by ejecting air from his spacesuit. Okay, Hollywood physics grade of D. At the estimated speed of Watney from the escaping air in his suit, his velocity would have increased by only half a meter per second or so. Okay, this is about 2 hours and 7 seconds into the movie. Let's assume that the Hermes is traveling approximately parallel to the MAV for some period of time. At such time, the intercept range was 312 meters. This is from the movie. So Watney has to rise that high while traveling approximately parallel to the Hermes at 850 meters per second. Can Watney be the spacecraft generate a vertical velocity component to travel 312 meters in a reasonable period of time? Okay, so the volume of the human body is about 0.07 cubic meters. Okay, humans have a density close to 1,000 kilograms per cubic meter. So if a human has a mass of 70 kilograms, right, you can use the density is equal to mass over volume equation to compute this 0.07 cubic meters. Okay, so now we multiply this by the density of air. I'm assuming that the entire body is composed of air, right? Because I'm trying to estimate how much air is in his spacesuit. And I don't know how much distance is between the spacesuit and him, so I'm being pretty conservative. I'm assuming he's full of air. Okay, so I'm going to multiply the density of air on Earth and in the Hermes and in the space station by the volume, and I get 0.085 kilograms of mass for an estimate of the air in the spacesuit. Okay, so now I can use mass. I can use the conservation of linear momentum equation to determine the velocity of Watney as the escaping air left the suit. So 0.085 kilograms times the speed of the air escaping the suit, 422, as I used in the previous example. Divide that by 70, and I get only half a meter per second of Watney's velocity going up as the air goes out. The other thing I'm assuming is, I believe he cut the suit right here. I'm assuming he's perfectly angling the escaping air down, so he goes up, right? If I remember, initially the air came out this way and he went down, and then he started to get the trajectory right. So I think this is being generous, because by the time he got the trajectory or the angle of departure of the air right, he probably lost a lot of the pressure. So I think this is probably on the high side, 0.5 meters per second. There he is. Okay, so all I've done here is it's a really simple equation. So distance is equal to speed times time, right? The speed of Watney is 0.512 meters per second times t. It's got to get to 312 meters, right, to meet the Hermes. So let's say he's here, the Hermes here. They're gonna, by the time he gets this altitude, he wants to have intersected with the Hermes. So if you solve for t, it'd take him 609 seconds to travel that 312 meters at 0.5 meter per second. So in the movie, it looked like it happened in about 60 seconds. Okay, this would be more like 10 minutes. So certainly it's possible for escaping air to generate enough velocity to go up, but it could take a long time. And I think this is probably on the low side. So Hollywood didn't do such a good job on that. The escape velocity of the MAV is required, so Hollywood Physics grade of A. So at 144 into the movie, it was stated that the escape velocity of the MAV would have to be reached in order to intercept with the Hermes. Presumably this was due to the estimated intercept point between the Hermes and the MAV. So did the MAV hit escape velocity? The speed of the MAV near burnout was 850 meters per second. That's given in the movie. So how much longer of a thrust to acquire escape velocity at 5,015 meters per second? So at 850 meters per second, the MAV was still experiencing thrust from a remaining booster. You can see that in the movie. Okay, so the MAV has to get to a speed of 5015 meters per second, and that's the escape velocity for Mars, and I'll show you how to compute that in a second. Where the initial velocity is 850, and the acceleration is 120 meters per second squared. The way I computed that is 12 Gs. Okay, so I think I'm being conservative here. It was stated in the movie that the acceleration of the MAV, I heard it in a couple different spots, 10 Gs in one spot, I think 12 in another. So if you this would be the acceleration, so 120 meters per second squared times time. So how much time at this kind of acceleration would get you to 5015 meters per second, and that solving for t here would give you 34 seconds. So that's pretty plausible from the movie. So how do you compute the escape velocity from Mars? So it's this equation right here. That's 2 times the constant g, which is 6.67 times 10 to the minus 11, times the mass of Mars divided by its radius. And this can be, I derived this in my book, and it can be derived from conservation of energy. It's really simple, actually. Okay, so that's how you get to 5015. So that's very, very possible, given the information in the movie, that from the continued thrust of the MAV, it could have made it to escape velocity. Okay, so that pretty much wraps it up. If you have any comments, send me the comments. And subscribe. I mean, I do this kind of stuff frequently. Thanks for watching.